Hi, welcome back. Last time we talked about the initial part of programming the SIR model. We set up our system object that has all the system parameters, including our initial state of our um, distribution of people into the different classes, whether they're susceptible, infected, or recovered. And now what we're doing is we're going to create the update function that goes from time t to time t plus 1 by using these dynamics that we determined made sense in terms of the differential equations governing the way that people transition between the states. So now we're going to take these differential equations and put them into Python code. All right, so let's now consider the setup. So we're at a particular state. We have some distribution of people into S, I, and R. Right? This is a state object, and we're pretending that we're at time t. So we want to take this and we want to pass this into our function. And after we have this whole function, then what we'll want to do is we'll want to pass out the state function at time t plus 1. We want to get the new state object that has the new S, I, and R in it. So this is the setup. We want to create a function which we will call update function. And it's going to take in the state, the current state, and give out the future state. So here's what we do. So the first thing we're going to do is we need to collect this information. We're passed in this object called state, and we need to create some local variables. All right, and so what's passed in is capital S, capital I, capital R. And what we'll do is we will capture that information in lowercase s, lowercase I, lowercase r. So S, I, R is equal to state. Now, in the past, I've had issues with this collection, with using this as a as the way to collect these variables from the state object. And what that had to do was that this state object had was kind of out of order. So even though it was defined in terms of S first, then I, then R, somehow the variables were out of order. So if in the end the code that we're working gives you really wacky results where the S and I and R kind of all are bouncing around a super large amount, then you'll need to replace this code by S is equal to state dot S, I is equal to state dot I, and R is equal to state dot R. So you might think of this S comma I comma R equals state as a shortcut for doing this set of 3 lines of code. If you end up with issues in your code, then you may want to replace this one shorter line with this longer set of 3 lines. But once we do this evaluation, then what's happened is we've created our local variables that keep track of the input that was passed in. So now that we've created the local variables, then we can use the system parameters to calculate the changes. So as you remember, we had the transition from S to I to R was due to infection. So we have some number of infected people, and we have some number of recovered people. So the number of infected people is equal to system.beta times I times S times I times S. We have the number of people who are infected, the percentage of people who are infected, the percentage of people who are susceptible, multiply those two by beta, and that gives how many new people were infected. Similarly, the number of recovered, we need to keep track of system.gamma times the current number of people, percentage of people who are infected. And so these are basically the changes in our SIR model. Those are keeping track of how many people have transitioned from S to I and from I to R. And then we use that to implement the differential equation. So we take S and that's equal to S minus the number of people who are infected. And then I is equal to the number of people who were infected plus the new people who got infected minus the people who recovered. And then R is equal to R, the number of people who had recovered, where we add in the number of people who are newly recovered. All right, and so this is now implementing that differential equation. And now we need to give this information outside so that we now can simulate from time t to time t plus 1. So we're going to now return a new state object that has this new information. Oops, that shouldn't be a bracket. State where capital S is equal to the new little s, capital I is equal to the new little I, and capital R is equal to the new little r. And so then this returns the next state. All right, and so we now have an update function that will start at time t, give us time t plus 1. And what that means is we can use a for loop to determine the final distribution. And so we can determine the final distribution, and just like in our other projects, we can then do something with that information. So at the end of the simulation, we can evaluate to determine our metric that we care about. We can use this to determine the metric that we care about. All right, so let's go and do this over in Python. All right, we're going to head over to Python. So here's our Chapter 11 notebook. You need to install Pint if necessary. We need to import all the information from the ModSim package. And then as we get down here, we have some initial state, which is 8910. And when you divide out by the total number, that's saying that 99% of the population is susceptible, and 1% of the population is infected, and 0% are recovered. All right, and so given our beta and gammas, we can play the make system beta gamma game, and this creates our system object. It has the initial distribution of people into the different categories. We have our end time, so there's 98 time steps. We have beta, which we're starting out with this 0.33, and we've got gamma 0.25. We're saying that every 4 days somebody gets better. All right, so excuse me, and so we have our update function. This is what we just defined. The update function says take in the time t, the state, the current state, and our system object, and define our variables, calculate the changes, apply the changes, and then return our state object. So that's our update function. And so if we look at what happens if we apply our update function once, so at time 0 to our init object, then what we get is that after 1 day, we have that 98.5% of the population is susceptible, and 1.2% of the population is infected, and 0.003% of the population is recovered. Now, these numbers, like, how can you have 0.003 of a person? Like, that's less than one whole person who's recovered. Well, remember, these are representing percentages over time. Actually modeling individual people is not the way we're approaching this simulation. So you'll have to do some rounding. You'll have to do some realizing this is all approximating. Right, and so if we wanted to, we could model what happens for over a number of different steps. And so we can create a for loop. So in this for loop, we would say we're going to let t start out at 0 and go up until the end time. And we're going to apply the update function. And as we apply the update function, it goes from time 0 to time 1, time 1 to time 2, time 2 to time 3. And this has all been wrapped into one run simulation object. And when you run it, it goes all 98 days. And it shows us that at the end of the day, at the end of the time, 52% of the population is still susceptible. Less than 1% of the less than 0.1% of the population is infected, and 48% of the population has recovered. So basically, either you're susceptible or recovered. There's not enough people infected anymore. All right. So the next step would be to visualize this, see how these populations are changing over time. And why don't we do that in the next video? All right, see you shortly.